maybe this slide. So we want to take into account let's say the maximum of the patient information to give a personalized prediction, let's say, of time to event for some health event of interest. And the objective is then to adjust the treatment of the patient, for example, or maybe put the patient in some groups of patients with the same characteristic to adapt their follow-up and so on. And the idea is really to develop methods that use the complete information. And in particular, we would like to incorporate time-dependent markers history into machine learning methods such as random forest, which are originally developed in the case where all observations are independent from each other. So let me present you quickly the individual dynamic prediction problem. So let's assume that we follow a patient and we measure a marker several times during the follow-up. And the idea is that, for example, here we have two measurements. We will define a landmark time at time 2. And what we want to perform, given those two measures, is to predict here the event-free probability of some event given for a certain horizon time. So I collect information from baseline to my landmark time, and then I have to predict what is going to happen for a certain horizon time here of 2 years. Let's say that those are years on the x-axis. And the principle of individual dynamic prediction is that now if I wait a little longer, I have another measurement there. So if my landmark time is now on 3 years, I have more information and I can again predict the event-free probability or update this probability. So given the fact that my patient is still alive now, and I have all those information, and so on, I have a fourth visit. Oh, sorry. What is this? Do you see some red lines on the slides?
Yes, we do.
I don't know how this happened.
Is that when you move the mouse in some way you were drawing?
Yeah. Okay. Maybe erase all. Oh, okay.
Okay, that's okay.
Sorry about that. Okay. Yeah. And so now the idea is that for this objective, several statistical methods are available, but usually they are quite restrictive in terms of the number of markers that they can deal with. So usually, for example, the joint modelings are able to handle a couple of markers only, and our objective, so this is, I don't know how this is happening. Okay, so we have someone who is hijacking the. Maybe Raquel, if we don't wait for anybody else, you can close the meeting.
Yeah, maybe I can do that. So how can I close it?
I can you or you
take me the
can
host to me. Yeah, I send you the host again.
as you wish, or maybe you can just apply the waiting room, and then you do not let anybody enter again,
Yeah.
or maybe somebody you don't know.
I can just try it. Okay. Okay. Okay, you can please go on and I'll try to do this.
Yeah.
Okay, thank you.
Okay. So yeah, so here, for example, I just update my plot with several markers. So I have now 6 markers, and I want to develop a method that is able to take all this information into account in order to have the best prediction of the probability of the event as possible. So what we can do, what already exists in the literature, is what is called the landmark approach. So here for the landmark approach is quite what I described earlier. You fixed a landmark time, which is denoted here by the vertical line. You collect all the information until this landmark time. You modelize and do whatever you want with those information, and then you predict what is going on after the landmark time. So the idea is that the fact that you stop considering data at the landmark time, it means that you will not use all the information for all the follow-up, and you will need to re-estimate all the things every time you change the landmark time. So another way to do this is to use a regression calibration model. So this is a 2-step method. Here you will take all the information into account, but you will not take into account the dropout information. So instead, you will have some biased probability at the end. So another approach, which is the good approach actually, is what I already mentioned, is to perform joint modeling, where you jointly estimate the longitudinal and the survival process together, and then you will end up with compute your probability of experiencing the event. And the drawback here is that you cannot use as many markers as you want. So our aim is to, let's say, go as close as possible as the joint model philosophy, in terms of really taking the longitudinal and the survival data completely in all the during all the follow-up. And we want this method, our method, to be able to consider many markers. So our main objective is hence to predict an alpha event using time-fixed covariate and potentially a large number of time-dependent markers, really using all the information. And so we are going to use the random forest principle. So this is the random survival forest already exists since the paper of Ishvaran in 2008. So it is a good tool for prediction. it is also able to handle high-dimensional data. And also some potentially complex relationship between the predictors and the events. However, it cannot deal with the time-dependent markers. Okay, so it's really is only tailored for taking into account time-fixed covariates, or maybe your markers, but are at only one time, and do not account for all the trajectories of the markers. So we would like to extend this method in this case. So just to give a quick overview about random forest, or at least the main principle behind the method. So the idea of random forest methodology, which was introduced by Leo Breiman in 2001, is the following. So you start with your data set, here denoted Dn. You have a first step of bootstrap. So you resample your data by drawing different bootstrap samples. And then on each bootstrap sample, you will build some randomized decision trees predictors. So you then end up with the collection of decision trees. So each tree will be able to predict your outcome. And then you aggregate all those trees, so all those individual predictions, all together to get the final prediction given by random forest. So the main idea of this method is to take a method, prediction method, which is a decision tree here, and to build a collection of randomized versions of this predictor, and then aggregate. So in a way, you will explorate the space of all the possible predictors more if you build, let's say, 1,000 trees instead of only one, and then you will aggregate, so kind of average all those individual predictions to stabilize the results. So I will detail what is a decision tree in our case for a survival tree, and then show how our random forest methodology will be able to take into account longitudinal markers. So one tree looks like what you have here on the right. So the main principle of the tree is to recursively partition your input space in a binary manner. So the algorithm works like this. You start with all your data in the root node, which is at the top, node number 1 here. You seek for the best way to separate this node into two child nodes. So the left one, the left child node here, number 2, and the right child node, number 3. And when you are looking for the best way of separate your node into the two child nodes, you actually optimize the criterion, and your criterion that you want to optimize is associated to your prediction problem. So for example, if you are in a regression, so you have an outcome which is just one quantitative variable, you will want that the variance of the outcome to be as small as possible in your two child nodes. And then once you have found the first split here, you do it do perform the same algorithm again for splitting this node into two child nodes, and again, so you have the recursive nature of the method here. And at the end, let's say that it is your final decision tree here. What you will also need is a way of summarize the information for all individuals which belong to a given node here, which is called a leaf. So a leaf is a terminal node with no childs. And again, your leaf summary will be associated to your prediction problem. And so actually, if you have those two ingredients, so you know how to split a node into two child nodes in a clever way, let's say. And if you are able also to summarize the information about all your individuals given in a given leaf, then you can perform a decision tree and then a random forest. So in our case, what we want to do is to adapt the splitting criterion to be tailored for the survival data that we have to predict. So now I detail now the splitting rule that we will use in our random forests. So our methodology is called DynForest, for dynamic forests. It is actually an R package which is available on CRAN now, just some weeks ago. It's kind of fresh. So the idea of the splitting procedure is to find two groups of individuals. So it will be our two child nodes with the largest difference in terms of survival. So the procedure is the following. First, you randomly select a certain number, which is called mtry predictors. This will be an important parameter of the method to keep in mind. And this is actually why the random forests are called random, is because of this randomized selection of predictors at each node before looking for the best splits. So you select completely randomly a set of predictors, and then you will consider for one given predictor, you will consider your two groups according to different threshold values. And for each value, you will compute the risk difference using either the log rank if you are in survival, or the fine and gray statistic if you are in a competing risk framework. So here, for example, on the left, you have a box plot of the value of one predictor. And on the right, the cumulative incidence function associated to the two groups. So let's say that the blue one is associated to individuals which have a value of the predictor less than the threshold, and the red one, the groups of individuals with a value larger than the threshold. So it gives you a certain difference of risk of experiencing the event for these two groups. And what you want by varying the threshold is to find the threshold value that will give you the largest difference. Okay, so you want to separate at the best as you can do people with, let's say, high risk of experiencing the event from people with low risk of experiencing the event. And the idea is that all along your tree development, you want your nodes to be as homogeneous as possible here in terms of survival. So you try several splits, and then you find the best one, so the one that maximizes your risk difference here. So now you have splitted your first node into 2 child nodes, and then you start again for splitting the left child node and the right child node, and so on. So this will be applied lots of times actually in your random forest strategy, because you will have several splits in your tree, and then you have several trees, and then you apply it quite a lot of time, this strategy. So this was, sorry, I didn't mention it, but this was for time-fixed covariates, okay? Because I can do a box plot here, so I have only one variable, which is time independent. I just have, let's say it's the age of your patient at baseline, for example. So you can just compute this box plot, try several threshold on the age of your patient, look at the older patients against the younger ones. And now maybe it's the core of our proposal here is how we deal with time-dependent markers. So we are going to use summaries actually of mixed models. So the objective here is to be able to extract some time-fixed features from time-dependent markers. Okay, so we want to from our marker measurements, which are trajectories here, we want to build some time-fixed features which summarize the variability of the characteristics of the trajectories here, and then we will apply the same strategy for splitting, but on these features. So what we did here is that we apply mixed models, okay, to model the trajectories, so one by one. So for example, the orange or red like on the top here, we apply mixed model to modelize this evolution. And then we compute individual random effects. So here we have several random effects. So the number of random effects will vary according to the model that we use. So for example, if we use a linear mixed model, we only have a random intercept and a random slope. But if we use some splines models, for example, we can get 3 or even more random effects associated to the different parameters of the model. So actually, we summarize the trajectories by those individual random effects with a certain number of random effects per markers. And then we will use those features as time-independent features to be able to split on them. So let's say that we now know how to split nodes with all kinds of predictors, so the time-fixed predictors and the time-dependent ones. Then we have to define a stopping rule. Okay, when we are going to stop splitting the nodes to the subgroups of data into 2 subgroups and so on. And what we did after some studies about these splitting rules is that we actually were using two different information. So the first one is the number of events of interest in a node. So we want to get a certain number of minimal number, to keep a minimal number of events in a node to perform the split, and also the number of subjects. We don't always want to split the node again and again. If we have, let's say, less than 4 or 5 people in a node, maybe it's not worth it to split it again into 2 child nodes. And then the final ingredient is to now that we have our tree, is to summarize the information about individuals on a given leaf. So here we use the cumulative incidence function estimated by the Aalen-Johansen estimator, only on individuals that belong to the leaf of interest. Okay, so for each leaf, we look only on the individuals that are belonging to this leaf. We apply the Aalen-Johansen estimator, and this will be what we are going to use for the prediction of the probability of event. So once we have constructed the tree, we can perform some prediction. So let's say that you have a new individual. You observe this individual until a certain landmark time, and you want to predict the probability of event-free at a given horizon time. You have all the time-fixed covariates, you have all the time-dependent markers collected until the landmark times. And then what you can do is compute the individual random effects for this new individual according to the model that you used in your tree. You have already the time-fixed covariates, and then so you can let go down the individual down the tree, given is variable. So, for example, in the first tree, the individual always start at the roots. Let's say it goes to the left, then again to the left, and it fall down to the leaf number 4 here. And attached to this leaf, you have the cumulative incidence function that we computed just before. And you do this for each tree of the forest. So let's say that for the last tree, your individual goes to the right, and then to the right, you go in, you end up in leaf number 7. Again, you have another cumulative incidence function computed here. And then you will take the average of your cumulative incidence function estimators of all your trees to get the aggregated cumulative incidence function for this individual, and then you can deduce its probability of event-free here to not experience the event at a given horizon time here of 2 years. Yeah, I don't know. Maybe if you have some question at this point, I could take a question or I go on with the. Yeah, do you prefer to just keep the question for the end, or? No.
Yeah, well, I think yes, because it's like 85 now. I think you can go on, yeah, unless anyone in the attendance can really stop now and ask anything. But no, I think that yes, you can better go to the end. Thank you.
Okay. Yeah, I now just want to illustrate the method on the simulated data. So here I have a simulation framework. We simulated 500 individuals. We repeated all the simulations 250 times. We have two time-fixed covariates, one continuous and one binary. And we consider either two time-dependent markers, and I will call this scenario small in terms of dimension. Okay, so a scenario where a joint model can be applied. And another scenario with 20 time-dependent markers, which I will denote by a large dimensional scenario in the following. So the markers are generated with the linear mixed models according to 4 latent classes and with either linear or non-linear trajectories. The risk of event is given by a proportional hazard model with a variable baseline hazard function. And we put some nonlinear dependence function on some predictors random effects. So we would like to see if the method is able to predict to give good prediction in this in those scenarios. And to measure this good behavior, we will compute the Brier score, time-dependent Brier score, and also the AUC to have an idea of the performance. So this is what we get in the small dimension case. So here the link between the probability of event is on a random forest, and we also add a 2x2 interaction between the random effects. So we have something which is not linear because of this interaction. And is in this small dimensional context, we can actually apply JM base, for example, which is an implementation of joint modeling, and compare the performance with our approach, which is denoted by DynForest. And as you can see there, we make the parameter mtry vary. So here from 1, which is the smallest value, to 4, which is the largest value, because we only have 4 predictors in this scenario. So on the left, you have the Brier score, on the right, the AUC, and you have every time 2 horizon times, so 1 year and 2 years, and 2 landmark times, S 2 years or 4 years. So if you look on the left, what we can see that the mtry parameter is quite important, even in this, let's say, a simple case, because if you take mtry with the too low value, you have a relatively poor performance in terms of Brier score. And actually, in all those examples, the best choice is mtry equals to 4. So in a way, you are not perturbing a lot your decision trees, apart from the bootstrap resampling, which is made ahead of the tree building. And now, if you compare with the JM base, we see that we get some gain in terms of Brier score, essentially in the S equals 2 case here. And if we look at the AUC, the IUC maybe are more comparable, and all the methods are quite with the same performance in terms of IUC in this case. Just to show you another scenario where now the nonlinear link between the probability of events and the predictors is through a latent class membership. Again, you have the same effect on mtry. You have quite a large gain here for DynForest compared to J-embeds in terms of barrier score, not so much in terms of IUC. And maybe I have to insist on the fact that here J-embase is misspecified because we do not assume a linear link between the probability of event and the predictors. So we are in small dimension, but in a complex relationship between inputs and output case. So it's not so it's kind of natural that we can do better than a J-embase. And now, just to show you some results in a large dimension context. So now I have 20 markers, and I take all those markers into account. Now I cannot compare anymore to J-embase because it do not run. And so here we only compare with the regression calibration method, which is a two-step method where you model all your longitudinal markers for all the follow-ups, compute some summaries, and then apply your survival method to predict the probabilities. And so here, again, with the interaction scenario, we have some gain in terms of barrier score and IUC, and even more in the latent class membership case, where here actually the regression calibration model is give really poor performance, more precisely in for IUC. So just let me finish. Maybe I'll be quite quick here to finish in time. We have also an application on real data to predict dementia in elderly population with death as a competing event. So we have more than 2,000 individuals in the cohort. We measure 24 time-dependent predictors, which belongs to groups of variables. We have cognition predictors, the predictors that measure the depression, the dependence, the cardiometabolic variables, and also some information which is based on MRI. And our aim, and we have also time fixed covariates as the sex, the age, and maybe the BMI. And the objectives here was to provide a tool to predict dementia. We fixed 2 landmark times, so S equals to 5 and 10 at an horizon time of 3. And we also want to understand which predictors is the most important in this task. So here are the results, but here we did not compare the performance, but just to show you that in this case, the IUC is quite reasonable. So we are kind of able to predict dementia in this case. And it seems that the task of prediction is easier at the landmark time of 5 compared to 10. And just to finish, what we can also compute using our package is this kind of plot, which represents the importance associated to the different predictors. So here you have all the predictors that we have colored by according to their belonging to these groups of variables. So some variables are time fixed and some are time dependent. Here what we see is that we have the IAGL, which is a measure of the dependency of the elderly people. And then we have some neurodegeneration variables and vascular variables, which are the most important variables. And maybe my last slide. We can also compute the importance of the variables, but according to the different groups. So maybe to have a more clear image about what dimension of the variables are the most important. And yes, so maybe I stop there. You have the air package, which is available. I didn't update it. It's now available on CRAN. You have this parameter, which is really important to tune. And we have some future developments, and I give you just some references. Thank you.
Thanks very much, Robin, and congratulations for the nice talk and very, very interesting work. I'd like to open now the turn for the attendants. If you want to ask anything to Robin, please, you can just raise your hand and you'll be able to make your question. So please, any questions? So any question or a comment for Robin? See that everything was very clear.
Hi, can I ask a question?
Yes, of course, Diana, please go.
Yes, hi, thank you. Thank you for this presentation. It's really interesting and a very good algorithm. I think it's a quite clever way to get all the information dynamically. I just wonder, why is it, why do you think the 5-year and 10-year points that for dementia study, why is the 5-year point was easier to predict than a 10-year? Because I thought that at 10-year, you have 10 years of data and 10 years of like history of all the markers. So it kind of should be the other way around.
Yeah, but actually, we also do not have, we do not have the same population at 10 years because we have for those elderly people lots of deaths between in this interval. So yeah, I'm not really sure to completely understand this phenomenon, but maybe you have kind of older people with maybe a more more diverse trajectories in their elderly behavior, and yeah, maybe the task is harder because of the on the fact that you lose quite an important number of individuals in this case because of the deaths, and then you have less people in your data, and maybe they are more heterogeneous on the later scale, something like this. I don't know.
Thanks very much, Robin. Any other question for our speaker?
I think Daniel asked something on the chat.
Yeah, I'm gonna see now. Sorry. Okay, so the question, thanks, Diana. So Daniel was asking, how many data points do you need for the longitudinal data to fit a random effects model?
Oh yeah, actually what we need is at least one observation per markers for all individuals. Obviously, if you have to have a good modelization of the trajectory, it will be better to have at least four or five time points. But even with the very low number of time points, actually it could run also. So, and yeah, I can also add that we tried it in another application where, at the contrary, we get lots of time points, and it was quite long to run, and maybe it's another challenge here.
Wait, sorry, because my computer is now very lazy and I have some problems to access the chat, but I can see another question from Erin Templeman, and the question is, did your data set contain any censoring? I think that's an important aspect as well. And if can this be something to adjust for with your algorithm?
Yeah, I think the censoring is taken into account in our method, because when we compute the prediction of the probability of experiencing the event, here we take into account the right censoring, and the fact that people are leaving the cohort and something like this.
Okay, thank you. There's still another question by Diana. Do you think that the method could also handle non-proportional hazard scenarios?
Yeah. Actually, we do not make any assumption of this kind, because our approach is kind of a non-parametric approach, in the sense with random forest, you do not impose a model like this. What we did is in the simulation study, we simulate the data according to a proportional hazard, just to understand what's going on, but we could generate with other scenarios, and we do not have to make any assumption of this kind yet.
Mm-hmm. Okay, there is another question by Erin related to the previous one on censoring, and she's just adding, so just to confirm, sorry, so it takes into account right censoring but not left censoring. Would this be an addition for the future?
Yeah, so I must admit that I'm not the best specialist about survival data. I'm more on the random forest and machine learning, but I had a discussion on this subject with my colleagues, and I think one of the development that we had in mind was also to take into account interval censoring, where you take into account that the fact that when you observe something, it's after a certain point and before another one, but you don't really know where you are. but as I understood the discussion, it was kind of hard in a way in terms of computational demand to incorporate it in the random forest strategy. So I think in theory we could do this, but in practice it would be difficult to implement it in a performing way.
Thanks very much, Robin. So,
sorry, Robin,
yes,
can I ask, like can I ask a very stupid question? So about the trees, the dynamic, so the trees that are built, are they specific for a landmark time or they are for any time?
Yeah, no, the tree are for any time. Because we have kind of a joint approach. Yeah, we do not define a landmark time when we build the trees. So we use all the information during all the follow-up to compute the splits in our trees. And once we have the tree, we are able to predict the probability of experiencing the event up to a certain landmark time, but the trees themselves are not associated to a fixed landmark time. Yeah.
So when so for example, when the time dependent markers they change, so does the person fall into different leaf of the tree or no?
Yeah, what you are going to do is to the individual that you have to predict will go to one leaf or another given his evolution of the markers. Yeah, I don't know if it was a question or.
Yeah, sure. Okay, so it's not like a person always falls into one leaf. It's dependent on how the dynamics of the covariates changes. They move from one leaf to another.
Yeah.
Okay.
Exactly.
I see. All right. Thanks.
You're welcome.
Thanks very much, Diana, for your questions. So I think that if there are no more comments or questions, we will finish the talk here. Thanks very much, Robin. And
thank you
again.
Yeah, thanks a lot.
It was really great to have you here. Okay, and then we will be back in December for our last meeting of the year. So please be aware of the email and the Twitter where we will be announcing the next speaker and date. So thanks very much to everyone for joining and enjoy your evening. See you soon. Bye, everyone.
Thanks a lot. Bye-bye.
Thank you.
Bye.